All right, guys, here we go. Second topic of 2.6. We're talking about bounds on the real zeros of polynomials. This is using the theorem on bounds. So here's what the theorem says. It says, suppose p of x is a polynomial, just like we've been dealing with for a while, right? And then with the real coefficients, and this is almost not worth mentioning because we pretty much exclusively deal with polynomials that have real coefficients. But here's a kind of important piece. The leading coefficient is positive. That means like the largest degree term is positive, okay? Okay, so supposing all that is true, and you run synthetic division by x minus c. Remember, when you run synthetic division by x minus c, that means the c goes in that little box. The coefficients for the polynomial go here. You pull the thing down, and then you multiply, and you add, blah, 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 right? But the important part is that c here is the thing that goes in the box, right? X minus c is what you're dividing by. Well, if your c is positive, bigger than 0, and all your terms are non-negative, then that means c is an upper bound. And what is an upper bound? It just means that any other zero has got to be smaller than c. Okay, what if c is negative and all the terms in the quotient alternate in sign? So alternating sign in the result. Then that means c is a lower bound. So that's the opposite, right? That means any zero has to be bigger than that c. So what's going to result? You're going to have one negative term and one positive term. All your zeros have to be between those two terms, those two c's. Now, again, another thing that I think is kind of like a fact to be memorized here, in math, like if you understand the theory, the proof behind the thing, then maybe you have a better conceptual understanding. But that's kind of beyond the scope of this class. I think maybe if you were to take upper division math, then you might learn it eventually. But right now, we're just kind of learning this as a fact that someone else proved already. And so we're just memorizing a fact. And in fact, maybe another case for learning mnemonic, right? So I recommend thinking of your own mnemonic. Here's kind of not really a good one, but here's one anyway. So let's say you divide by c, where you run your synthetic division. Maybe I'll just draw a little c for myself to remember. And let's say it's non-negative, then I'll say that means you've got an upper bound. So n equals upper bound, or nub. You divide by c, you do the synthetic division with c, and n means upper bound. Or let's see, the other half is if you divide by c, or x minus c rather, and that means you run the synthetic division with c. This is a negative number, right? Maybe adds a little caveat here too. So this is c greater than 0, c less than 0. And then you end up with something that's as alternating sign, then that means you had a lower bound. Okay, not a very good mnemonic, like I said, but something, right? And you can think of your own to help you memorize it, whatever helps you memorize it. Okay, let's go to the questions. We're looking at 3 and 4. When I give you my mnemonic, that's just something that comes off the top of my head. Sometimes it might click with you, sometimes it might not. If it doesn't, then, like I said, better to think of your own, but kind of just to get your brain rolling in that direction for facts. That's think of some way to make it stick in your brain. Okay, here we go. Use synthetic division to determine upper and lower bounds on the real zeros of the polynomial. And real here because, like I said, we're just talking about real numbers. In the next video, we'll introduce complex zeros. Okay, so for here, I'm gonna actually start by looking at what are the possible rational zeros. So I got 21, I got 2. That means I've got p over q, where p divides 1, 3, factors of 21, right? 1, 3, 7, what am I missing? 1, 3, 7, 21, is that it? Yeah, actually that's it. And q divides 1 or 2. So that means p or q could be 1, it could be plus or minus 3, plus or minus 7, plus or minus 21, or it could be any of those halves, right? Plus or minus 1/2, plus or minus 3/2, plus or minus, what is that? 7/2, plus or minus 21/2. Right, those are all possible roots. Okay, so what I'm gonna do, I could start with the smallest rational number to see if that will be an upper bound, but personally, it doesn't say to find the smallest one. So I'm gonna kind of just start with the whole numbers. I'm just gonna work with whole numbers, okay? And at least I'll get some upper bound. So let's start with the positive one. Let's start with 1. The coefficients are 2, -3, -14, and 21, right? Let me just divide this so we don't get mixed up. Okay, so I'm going to run my synthetic division. 2 comes down. 2 times 1 is 2. Add those together, I get -1. -1 times 1 is -1. Add those together, I get -15. -15 times 1, -15. And then -15 plus 21 is 6. Okay, I'm looking for the upper bound here, right? We're going to put a positive number here. But these guys are not all positive. They're not all non-negative. So 1 is too small. Let's move up to the next option, which is 3. Same coefficients here. Run the division algorithm. 2 comes down. 2 times 3 is 6. 6 plus -3 is +3. 3 times 3 is 9. And 9 plus -14 is -5. So already I failed. So that didn't work. So I'm going to go straight up to the next number. Actually, you know what I'm going to do, guys? I'm going to look at here. This 7/2 would be 4.5, right? So let's go to the next number that's above that. Let's go to 5. I'll do the same thing. 2, -3, -14, 21. Bring the 2 down. 2 times 5. Oh, sorry, 2. 2 times 5 is 10. Add those together, I got 7. 7 times 5 is 35. 35 plus 14 is going to be 19. No. 21. 21. Yeah. 21 times 5 is going to be way bigger than I need it to be. 105. It's going to give me 126. Okay, that means everything is positive, right? So for sure 5 is an upper bound. I'd like to find the smallest whole number, so I should have actually gone to 4, it looks like. Let me try 4. Okay, run the algorithm one more time. 2 times 4 is 8. 8 plus -3 is 5. 5 times 4 is 20. 20 plus -14, 6. 6 times 4 is 24. Right? Did I do my math correct? Yeah. 24 times... Oh, sorry. Add those together, I get 45. Okay, so you see all these numbers are positive, right? And of course, anything above that, so if I plug in 5, I plug in 6, it's always going to be positive from there on out, right? Anything above 4, in fact, is going to give me all positive numbers. So that means that 4 is actually an upper bound here. 4 is an upper bound. So any positive root is going to be smaller than 4. So 4 is an upper bound. Now, I haven't found the most restrictive upper bound necessarily. There's going to be a fraction that's going to give me a closer approximation. But I found the best whole number upper bound. And that's good enough. I should have maybe specified in the question to find the best whole number or integer upper bound and lower bound. But that's what I'm going to aim for here. Okay, let's go for the lower bound now. So 4 is the upper bound. I'm going to just erase so I can repeat this for the lower bound. Okay, just remember 4 was the upper bound. Let's go ahead and find the lower bound now. So lower bound time. Okay, so same function or polynomial, right? Now I'm going to check lower bounds. I guess -1 is the obvious choice to start with. 2, -3, -14, 21. 2 come down. 2 times -1 is -2. Add those together, I got -5. -5 times -1 is +5. +5 plus -14 is -9. And okay, already I see I did not alternate signs, so I'm just gonna stop already. Which is maybe something I should have done last time, yeah. Okay, let's see. Let's just go to the next whole number. This is probably not the most efficient way to do it. You know, I don't know. I take it back. Let's go to -3. And if -3 works, we'll go back to -2 to see if it works. Okay, bring 2 down. 2 times -3 is -6. Add those together, I got -9. -9 times -3 is positive 27. Plus 14 is positive 13, right? Yeah, and then times -3 is -39. Okay. So that's going to be 18. And negative 18. Okay, so here I am alternating signs, right? Positive, negative, positive, negative. So that means negative 3 is an upper bound. And since I kind of overshot a little bit, now we're going to go ahead and I overshot on purpose just to see what happens, right? Like you're trying to kind of get to the first place where you have a lower bound. And then once you kind of know you have a lower bound, then maybe go backtrack a little bit and see if the number before it was a lower bound as well. Okay, so 2 goes down. 2 times negative 2 is negative 4. Negative 7 times 2 is going to be positive 14. Which is 0. Which is 0. Which is 21. Okay, so I got positive, negative, and then non-negative and positive. So that one didn't quite work. So it looks like negative 3 is my best lower bound that's an integer. So negative 3 is a lower bound. So that means, according to the theorem, that any real zero is going to be between negative 3 and 4. So good news is we can say, okay, 7 is out. So is positive and negative 7 are out. Positive and negative 21 are out. 21 divided by 2 is 10.5. So those are out, right? And 7 halves is 3.5. So 7 halves is still a possible root. Negative 7 halves is not, though, because that would be lower than negative 3. So that kind of narrows down some of our options, right? Negative 7 halves is not possible. So if I was to go and check roots, then it tells me, oh, okay, these are the only possibilities right here for rational roots anyway. And as far as real roots, they're also going to follow these rules here. Any real root, even if it's not a rational number, it could be like something with a square root or something, still going to be between negative 3 and positive 4. So that's pretty cool. All right, we're going to repeat that same process for number 4. Same exact process. Okay. Okay. So here's 4. What am I doing now? Okay, so let's start by writing what are my possible rational roots. Things that P divides 4, Q divides 1, so I have only whole numbers, plus or minus 1, plus or minus 2, plus or minus 4. Those are the only possibilities. Okay. And let's run our algorithm let's start with 2 this time. And then if it's already an upper bound, we can check back to 1, okay? Okay, so 1, 3, 1, negative 4. If you don't want to do it the way I'm doing it, you can just do it systematically. Start from 1 and work your way up. But I'm going to just try to skip ahead. 1 times 2 is 2. Add those together. I get 5. 5 times 2 is 10. 10 times, add those together, 11. 10 times 2 is 22. And that's going to be positive. That is 18. Okay, so 2 is an upper bound. So what about 1 then? Let's check back to 1. Was 1 an upper bound? Bring 1 down. 1, 4. 4 times 1 is 4. That's 5. 5 plus 1 is 5 times 1 is 5. Positive 1. Oh, yes. So actually 1 is an upper bound. Which is great news. Great news, yeah? Any root's going to be lower than 1. Lower than, let's see. Is 1 a... Yeah, 1 cannot be. It's got to be lower than 1. Okay, that's kind of good news then, because that means I must not have any rational positive roots, right? So that's useful information for me. It means I'm not going to bother checking 1. I'm not going to bother checking 2 or 4. Well, I just checked 1 actually, and I just checked 2. But anyway, I wouldn't check anything. I wouldn't check 4 at least. If I had started with 1, I would have known not to check 2. Okay, let's go on to the negative ones. Why don't we start systematically with 1 now? Negative 1. 1, 3, 1, negative 4. Run the algorithm. 1 comes down, times negative 1. Add those together, I got 2. And already I'm not alternating signs, so I know negative 1 is not a lower bound. Let's go on to negative 2. 1, 3, 1, negative 4. Bring the 1 down. 1 times negative 2 is negative 2. And add those together, I get positive 1. It's not going to work already, right? In fact, I can kind of just look ahead and see that if I plug in -3, I have 0, and that wouldn't be a sign change either. So I'm going to go to the next viable option, which would be -4. My color scheme is all off here. I should have been alternating below, yeah? So let's do, sorry, -4. -4. Okay, 1, 3, 1, -4. Those are the coefficients. Bring the 1 down. 1 times -4 is -4, which is -1 when you add it. -1 times -4 is +4. Add those together, you get 5. 5 times -4 is -20, which gives me -24. So now I am alternating signs, which means -4 is a lower bound. Okay, so that means that -4 is out. Well, actually, I knew that from just doing it just now anyway, but anything above -4 is also not a possibility. So that's what the theorem says. -4 is a lower bound, and 1 is an upper bound. Okay, guys, that's it.